Log on, tune in, find out. Another good idea from Cambridge.
Seminar in the Syntax and Semantics, Legacy of Alan Turing. And there will be 3 talks this afternoon, the first of which is to be given by Ian Herbert. I keep seeing the screens out there, Mr. I. Herbert, as I guess one says here. And he will speak on lowness for information.
Okay. So yes, hi, thanks for coming. Thanks to the organizers for organizing this and inviting me to speak. So the title of the talk is Lowness for Information. I got an email last week that actually it's not called that anymore. So the talk is actually going to be about finite self-information, which is the same thing, but a different name. So I also, I'm not sure kind of what everyone's background is here, so I'm going to try to keep the technical details to a minimum, but also enough that it will be interesting to people who are actually interested in this stuff. So let's start off with some definitions. So we're going to be talking about information. A good way to talk about that is, I guess, for, say, sigma and 2 to the less than omega, right? So a finite string of 1s and 0s. The prefix free Kolmogorov complexity of sigma, sigma is, there are technical definitions. We'll just say the length of the shortest program that outputs sigma. Right, so choose your favorite programming language that is, not too odd, right? That can kind of do everything it should do. And then write a program that will, when it runs, output some string of 1s and 0s. So if the string is just 100 zeros, right, write a program that says print 100 zeros. If it's something more complicated, right, like 100 bits with 1s in all the prime places, right, you want to write a program that will be able to tell when a bit is prime and then print 0s and then print a 1 at a prime place and then keep going. Right, is that? Yeah. So, yeah. So then, let's keep going. For 2 such strings, we're going to say the mutual information on sigma and tau is the Kolmogorov complexity of sigma plus the Kolmogorov complexity of tau minus the Kolmogorov complexity of the pair sigma tau. So you want to think about Kolmogorov complexity as kind of a measure of how much information is contained in a finite string, right? So for example, a string that's just 100 zeros, there's not much information there, right? Kind of anyone can just generate 100 zeros. For, say, a string you get by flipping a coin 100 times, right? It's kind of randomly generated. You want to say that there's a lot of information there, right? It's kind of, the Kolmogorov complexity is going to be, well, the best you can do to describe it is to tell me, up to like an additive constant, what the bits are that you got flipping the coin. So there's going to be a lot of information there. And then this mutual information is, well, so to describe the pair sigma tau, the worst that can possibly happen is that sigma and tau have nothing in common. So you're going to have to describe sigma, and then you're going to have to describe tau. And in that case, there's going to be no mutual information, right? Because here's how much you need to describe sigma, here's how much you need to describe tau, and then you have to describe sigma and describe tau again, you get 0. So if they have nothing in common, they have no mutual information. that's kind of what you would like in a definition. If sigma and tau are the same, then to describe sigma and tau, you just need to describe sigma and then just say, and do that again, right? So that's, this will be just as bad as k of sigma. And then that'll cancel with that. And you'll get some information, right? However much information was in sigma is the mutual information of sigma and tau. And then kind of anything in between, right, can show up, depending on how close sigma and tau are. So this, I guess, I don't know if I should be citing people. Kolmogorov complexity was discovered by Kolmogorov. This mutual information, he was the kind of wanted to use it as a measure of information content of strings. Most of this early work is either Kolmogorov or Levin. There you go. So here's a good definition for mutual information of finite strings. It's kind of interesting, or we want to think about maybe how we would extend that to infinite strings of ones and zeros, right, reals. And we have a definition. This is due to Levin. It's not exactly clear that it's the best definition, but it has some nice features. For reals, the mutual information of A and B is and here's where things get ugly. It is the log base 2 of the sum over all pairs of finite strings 2 to the, let's see, k of sigma minus ka of sigma plus k of tau minus kb of tau minus k sigma tau. So, right, it's not clear at all that it has anything to do with the definition we have for finite strings. It is actually, this is kind of why Levin likes it. It's a theorem due to Levin that if A and B are finite, then these things are the same up to a constant. Which is why you need this log term, right? In general, this is an infinite sum. Kind of the things we'll be interested in are, is it finite or not? And putting a log in front doesn't change that. But if you want to get this, right, you're going to need to
What does it mean, k, when an a is in there?
Oh, right, sure. So k of sigma, right, is the length of the shortest description. K of A of sigma is going to be the length of the shortest description of sigma using A as an oracle, right? So kind of write programs that can look at A, and they might be able to do better than just a program with no oracle in describing sigma. So this definition looks awful. It has this nice property, but if we actually parse it in the right way, it might look like it actually makes sense, right? Kind of, we look at this. This is the information content in sigma minus the information in sigma kind of relative to A, right? So this is, say, it takes 10 bits to describe sigma, but A can do it in 7 bits. That means the difference is kind of roughly how much A knows about sigma. Right? Sigma is 10 bits of information. According to A, it's only 7, so that means A knows 3 more bits than anyone else does about sigma. Right? And this is the same. How much B knows about tau. Quotes. And then this last guy, right, is just the complexity of the pair, because we only want to count A and B as having mutual information if they have information about things that are closely related, right? If we're summing over all pairs, right? So if A says, I know a lot about snakes, and B says, oh, I know a lot about lizards, and you would say, okay, snakes are kind of like lizards, right? They probably have a lot of mutual information, right? The just Kolmogorov complexity of the pair of strings about snakes and lizards are going to be close. But if A says, I know a lot about snakes, and B says, I know a lot about doorknobs, you want to say, well, snake's not really anything like a doorknob, so this is going to be high, and kind of that term won't count for much in the sum. So this is the definition we're using. It's messy. It kind of makes sense. There have been alternate definitions proposed, also by Levin. So
Shouldn't there be a minus up there somewhere?
a minus.
2 to the minus?
So
Exponent can be negative.
It's got to be negative, minus k of sigma.
yeah, this term is going to
No,
be.
the first deleting term. When you would have a minus around the whole thing, or am I mixed up?
I'm pretty sure this is right.
A and B are
When A and B are
And the
empty, then the
first-
whole
the
thing
first
is negative
difference is collapsed.
k of sigma.
You end up with that big minus k sigma tau.
Yeah.
The k sigma tau is the thing that's the big negative factor.
Is there a definition like this just for the complexity of the single infinite string?
Yeah. If you think about it, if you try to just think about, you can look at like the Kolmogorov complexity of the initial segments of the string or something like that. And people have thought about that. That's kind of well understood. The ones with the least information are going to be what are called k-trivials. And those will come up. We'll talk about how that relates to this stuff. So Levin also proposed this definition, simplified mutual information. It's going to be the same. We got a log and a sum. It's essentially the same definition, but you only look at pairs where sigma equals tau. So that cuts out a lot of pairs. And if sigma equals tau, you just end up with k of sigma minus ka of sigma minus kb of sigma. Right? If sigma equals tau, the complexity of the pair is essentially just the complexity of sigma itself. So those terms cancel. So it's clear that, let's see, if this is finite, then this is also going to be finite, right? Because this sum is just sum of the terms from this sum. But so far it's open whether the converse holds. Sure. So it would be nice if we could get the converse to hold, because that means we could still study this, which we maybe want to study because it looks nice, but we could do it by actually looking at something that's simpler to look at and work with, right? It's also open if A and B are finite. Do we have that their mutual information is up to a constant, what we said the mutual information of finite strings should be. Because, I don't know, maybe if we don't have this, but we have this, then this is also a good candidate for an extension of the finite case to the infinite case. And maybe, they're not the same, but this is the one we're actually interested in, so this is the one we should worry about. So that's, I don't know. I've thought about that a little, but have not gotten anywhere. Everything, all the results that I'm going to mention are going to be true also for simplified information. So right now, we're not worried that we might have the wrong notion. It's okay. Essentially because we're only worried so far about cases where the first one is infinite, right? So A is finite self-information. It should be exactly how it sounds, right? If the information of A with itself is finite. So if it has finite self-information, it also has finite simplified self-information, right, just from that. So these are the kinds of things that I'm interested in. I do a lot of work studying them, gotten some results. Let's talk about a little bit about how they relate to other things that other people are interested in. So, for instance, let's see. A is k-trivial, if and only if, let's see, exists a C such that for any n, let's see, is no, I guess I don't need to see. So if the initial segments of A are about as complicated as, sorry, it should be K of n. If describing the initial segment of A is as bad as describing the number n, that's k-trivial. These are the things that people want to say are kind of the simplest cases, the things with the least information. The actual, just want to make sure. D. So the definition that I like to work with, because it's easier and it kind of is closer to the definitions we use for the things we're already talking about. This is actually called being low for k, right? It says that if you use A as an oracle, you can't get much better than what the descriptions were without any oracle, right? You can maybe, there's some constant that you maybe can compress strings up to that constant, but no better. And it turns out these are equivalent. And then it's kind of clear that if A is k-trivial, then it has finite self-information. Right, because if you look at this definition, you can move things around. You get that k of sigma minus ka of sigma is less than d. So if you plug that back into here, you just get 2 to the d plus 2 to the d plus d minus k of sigma tau. The 2 to the d's, are just constants. They can come out front. And then the sum of over all sigma taus of 2 to the minus k sigma tau, that's going to be finite, less than 1. It's going to be the domain of, for people who know and care about these things, right? That's the domain of some universal prefix-free machine. So it's less than 1. Sure. Let's go back up here. All right. So, this was noted by Levin. He asked the question whether that's exactly all of them, right? If everything that has finite self-information is k-trivial. This recently proved by Dennis Hirschfeld and Rebecca Weber. But that's not in fact the case, right? There exists an A with finite self-information. That's not k-trivial. And the way that they do this is that they, I'm not going to give the proof, but I'm going to tell you what's important. It uses this lemma that they show that there exists an F such that the sum over all sigma taus, let's see, 2 to the minus k of sigma tau plus f of sigma plus f of tau converges. And f has a computable approximation with, let's see, for any I, for all but finitely many sigmas, for any stage in this approximation, the value of sigma at that stage is bigger than I. So that value is on the sigmas go to infinity, kind of. There's only finitely many sigmas that ever get the value I at any stage in the approximation. And this, right, I guess that sum looks a lot like this other sum that we're talking about here. All right, so let's leave that up. But it's kind of clear, right, that
So it's like left CE or something like that, or is it? You said was it?
I think so.
Is it delta 2 or is it?
yeah, it's kind of long and involved. I don't want to actually go through the definition.
I'm just asking, is it
Yeah, it
left
is.
CE,
I think-
right CE, or delta 2?
I'm pretty sure it's delta 2. I could look. Yeah, it's something like it measures how close the approximation to omega is when sigma gets its shortest description, kind of in the enumeration of the universal machines. So, right. If we have some real k of sigma is less than or equal to up to a constant ka of sigma plus f of sigma for all sigma, then A has finite self-information. Right, that's just kind of, you can move that over and then plug this into that, and you get, it's bounded by that sum, and that sum is finite, so this sum is finite. So far, everything, this is the only way we know how to construct things that have finite self-information. So that's an open question. Is k of sigma less than or equal to ka of sigma plus f of sigma necessary? I'll do a constant. I guess a long time. Here's the result that I have so far is that using this f, you can build a perfect tree, right, where each path obeys this inequality. So you get there's a perfect pi 0, 1 class of reals with finite self-information. You can build the tree such that all the branches are the same except at certain coding locations. So you can code whatever you want into a real with finite self-information. And the tree, right, is recursive. Whatever, for anything above 0 prime, exists B and C with finite self-information. Such that A, B plus C, which is A is equivalent to the joint of B plus C. So this says, right, that as a class, right, the reals with finite self-information are very far away from the reals that are k-trivial, right? There's this result from Hirschfeld and Weber that there's at least one, but the k-trivials, there's only countably many k-trivials, right? The k-trivials form an ideal. There aren't kind of many of these, and they're very far from being an ideal.
Are these all like Lopez-Hausdorff dimension or something?
So that's not known. That's something that's open that I want to think about. You can certainly get, so that segues nicely into the next thing I was going to talk about, I guess. It turns out that in this proof, you don't use anything about f other than these properties, right? This is all you need. You just need an f that has a computable approximation that has this nice property about its limit going to infinity. And then you can build a perfect pi-0-1 class where everything obeys this inequality for whatever f you chose. And you can get, anything above 0 prime is a join of two things. So let's go up here. So in particular, if you choose your f to be f of sigma is the log of the length of sigma, then everything you get in that set is going to be low for effective Hausdorff dimension. So I don't know if I want to write that. I guess this is an open question, right? F doesn't really matter. So the question is, are there interesting f's that are going to give you this property for other classes of things that you were already interested in? No, maybe. Also, the fact that f doesn't matter tells you something about the class of k-trivials, right? So it says that this is far from the k-trivials, but it also says, right, let's write down this definition of k-trivial again. What are we going to say? Right, plus d. And we know we can get, for, let's say this, if we weaken this to, right, if we no longer require that it's only the same up to a constant, if we say, however we have some f that is however slow growing you want, as long as it has a computable approximation and it eventually, right, it goes to infinity in this approximation like that, then we get something far from k-trivial, right? If we weaken this, then we get uncountably many, and not an ideal. Right, so this says something like k-triviality is like the weakest notion for some reasonable sense of weakest, right? It's maximally weak and giving you something nice, right? It gives you a nice countable class that's an ideal. So I don't know, that's one last thing that I kind of would like to think about is what exactly are the properties of f that are necessary here? Right, because so what is like a nice one property of f that will give you this, right? All the time. And then you can say that, for any f like that, if you weaken k-triviality using that f, it becomes very far from k-trivial. I think I'm out of time.
Thank you. Of course, we've had a few questions already, but if there's one more quick one, we can certainly answer them. Well then, Ian, thank you again.